discussion about particle in a infinite potential box. So what we were discussing in the part 1 of this lecture uh, module, that the general solution of the time dependent Schrodinger equation is written as where psi n of x and t, where now wave function is your time dependent, is written in terms of Cn times phi n, which is your time independent part, times the time dependent phase part, which is e to the power minus I e n t over h cross, and this n goes from 1 to infinite. So what are you trying to do is to express this general wave function psi n of x and t in terms of the phi n and the corresponding phase vector, and the weightage of individual term is taken care by this coefficient Cn. Okay, so Cn in general is a complex coefficient, and for a infinite potential box, we know what is our phi n of x and we know what is our En. So once we substitute, we can express psi n of x and t as summation over n, where n goes from 1 to infinity, Cn times square root of 2 over L sine of n pi over L and times x. So this is your phi n of x, and this exponential part is written as e to the power minus I n square pi square h cross square over 2ml square times t over h cross. Okay, so the task is how to estimate or how to calculate this coefficient. This is where we have stopped our last lecture. Now to find Cn, it is easy to express first the general solution of your time dependent Schrodinger equation with t is equal to 0. So once we set t is equal to 0, then psi of x at t is equal to 0 is written as n goes from 1 to infinity Cn times phi n of x. Okay, and as we have put t is equal to 0, so the exponential t dependent part reduced to 1. Okay, so this is what we have written. Now this is I would say much easier to find Cn in this case. So what we are going to do, we will multiply psi of x 0 by phi m star of x from left. Okay, and then we will take integration from 0 to L over dx variable. Okay, so once we will do it, so let's multiply this quantity. So from the left hand side we have multiplied this, and it means that in the right hand side when we multiply phi m star of x, and we are going to perform integral over dx. Okay, so this is what we have done in the last slide. We know how to solve this part. So Cn is a coefficient, I can take it out from this integral. Now my integral is consists of phi m star phi n, okay, where integral goes from 0 to L dx, and this condition we have seen in the previous lecture, that this is the orthogonality condition. Okay, and this gives us delta of m and n, and this delta of m and n is non-zero when m is equal to n. So once you substitute m is equal to n, then this summation reduces to single number, and then Cn goes to Cm. So this is the value of your Cm on the right hand side. So for a given psi of x0, the way to find a coefficient Cn is to multiply this psi of x0 by phi n star of x and integrate over 0 to L dx. Okay, so this is the way to find the coefficient. Okay, now another question that you could ask is whether psi of x and 0 is normalized or not. Okay, so what it means, that if you take the modulus square of psi of x0 and integrate over space from 0 to L, it's supposed to give you 1. Okay, so let's check how it comes out to be. So to make the modulus square, first let's rewrite psi star of x0. Psi star of x0 will be Cn star phi n star of x, summation goes as it is. Okay, now when you take this Cn star and phi n star. In this one, they are the complex conjugate of Cn and phi n of x. Okay, so when you take the psi star psi, which is modulus of psi x0 square, it means that it will be Cm star phi m star Cn phi n. Okay, so let's take this equation. So it means that we can take it out, Cn star Cn, Cm star Cn outside. Now we have to perform this integral. Again, this is our known integral, what we have seen in the previous slides. Okay, this will give us delta mn, and delta mn is going to be non-zero when m is equal to n. So this will reduce it to mod of Cn square. Okay, so mod of Cn square is going to be 1 based on this condition if this wave function is normalized. So what it means that any general wave function of time dependent Schrodinger equation at t is equal to 0 is normalized, is that the normalization of psi x0 requires the sum of the modulus square of the coefficients to add to unity. Okay, it means that this mod of Cn square is the probability of measuring or finding the energy En in the general state psi of xg. So this is the meaning of mod of Cn square. Okay, so now let's look what is the energy of this general solution psi of x0. To know the energy, we have to operate Hamiltonian on our general wave function psi of x and 0. For this particular case, our Hamiltonian each consists of only kinetic energy part. So we have written minus h cross square over 2m d2 over dx2 times psi of x0. Okay, now we need to know what is our E times psi of x0. So we can express this psi in terms of the phi, and as our Cn is a constant or coefficient, then we can take this Hamiltonian and operate on our phi n. We know what is the value of this one when we have discussed this eigenvalue equation, because this phi n is an eigenstate of this Hamiltonian with eigenenergy En. Okay, so we can rewrite this part h times phi n of x is equal to En times phi n of x. This expression is not equal to E times summation over n C and phi n of x, because this is your psi of x0. Okay, so this h psi of x0 does not equal to E times psi of x0. It means that psi of x0 is not the stationary state. Okay, because this does not fulfill the eigenvalue equation. Okay, so it means that this is not the solution of time independent Schrodinger equation. This is the ultimate message that we have got. This any general solution of your time dependent Schrodinger equation at t equal to 0 is not going to be the solution of time independent Schrodinger equation. Okay, now let's estimate what is going to be the average energy of Hamiltonian in this wave function psi of x0. So to know the average energy, as we have seen that we have to take the expectation value of this Hamiltonian, which is average energy. Expectation value of Hamiltonian means psi star h psi. Okay, where h is our operator here, Hamiltonian is a non-operator, and we have assumed that the psi of x0 is normalized, so we don't need to normalize this form. Okay, we know what is going to be this one, we have seen in the previous slide. Okay, so we can expand psi of x0 in terms of the c and phi n. Okay, summation over n, and Cn is a coefficient, then we can take it out, h can operate here, it will be En times phi n. Okay, and this psi star of x0 is written as a Cm star phi m star and summation over m. Okay, so this is what we have got it. Okay, so now we can take both the summation outside of this integral. So now summation over m and n both goes from 1 to infinity, Cm star Cm, and this will give, when h operates on phi n, it will give us En, which is again independent of x, so we can take it outside the integral. Now what is left is the phi m star of x and phi n of x. Okay, and then we have to perform the integral. Again, we know what is this value of this integral. The value of this integral is delta mn, and when m is equal to n, then this value will be unity. Okay, so this is what we have got it. Now we can substitute m is equal to n, then it means that what we are going to get, we are going to get summation over n mod of Cn squared times En. Okay, so this is what we have got. The average value of your Hamiltonian is summation over n mod of Cn squared times En. Now let's try to do few examples. So the first example is given here as consider psi of x is equal to a times x times L minus x for x ranging between 0 to L, and this is an arbitrary state of a particle in 1D rigid box. Okay, you can see that this wave function goes to 0 when x is equal to 0 or x is equal to L, so it fulfills this boundary condition what we have seen. Okay, now so if we plot this wave function looks like this. I have said that it is 0 at x is equal to 0 and x is equal to L. Okay, and now the first question that we are trying to address is that what is the value of this normalization coefficient A. Okay, now to find A, we have to integrate mod of psi square dx between 0 to L. Okay, so when we do it, what we are going to get, mod of A square. Now this will be x square, this will be L minus x square. We are integrating between 0 to L dx. Now this is a simple integral that you can do by yourself, and by doing this thing you can obtain the value of A is equal to square root of 30 over L to the power 5. Okay, so we have obtained the value of this constant A, which is known as normalization constant. A is equal to this, so now we can substitute this value here. Okay, now another question is that how to write psi of xt. Okay, so we have seen how to write psi of xt. Psi of xt is summation over n Cn times phi n for a particle in a box times e to the power minus I Ent over h bar. Okay, now the question comes, what is your Cn? Okay, to find the Cn, we have seen that we have to multiply this wave function at time t is equal to 0 by some phi n star x and integrate over the space 0 to L, then we can obtain it. Okay, so this was the definition, as I have stated, that to obtain the Cn, we have to multiply this as t is equal to 0 by phi n star x from left, and then we have to integrate over entire space. Okay, so to do this, let's obtain, so this is your summation over Cn, or let's say the phi n. Okay, this is your phi n star, and this is your psi of x0 from the previous slide. Okay, and once you integrate over and do your mathematics correctly, then you will see that this value is 0 for even values of n, and this value is non-zero for odd values of n, and for odd values of n, the Cn is 8 times square root of 15 divided by n pi to the power whole 3. Okay, so this is the way that we have obtained Cn. Now let's move further. Okay, so we can substitute the value of Cn, what we have seen just now, and now you know that the summation over n is not anymore going from 1, 2, 3, 4 to infinity, but it is only restricted to odd values of n, because for the even values of n, your Cn is 0. So this is the general way of writing your psi of xt. Okay, so you can see that your Cn is proportional to n to the power minus 3, that you have seen it. Okay, it means that, okay, in psi of xt, the composition of phi 1 of x is 101 over 20, sorry, the composition of phi 1 in psi of xt is 1 over 27 times added, phi 3 is added to 1 over 125, phi 5 is added, so on. So it means that psi of xt is mostly characterized by the phi 1 of x, because this has the maximum contribution, then the least, and so on and so forth, because the contribution reduces drastically as n increases. Okay, now what is the energy of the particle in the state psi of xt? So we have seen that the average energy is written as summation over n mod of Cn square En. Now we know what is our Cn from the previous slide, and we know what is our En for a particle in a box, n square pi square h cross square over 2ml square. Okay, so once you simplify it, you can do the series summation. You will see that the average energy for a particle in this state comes out to 5h cross square over ml square. Okay, so we can see that your average energy is almost as E1. Okay, this is also true from the previous slide, that your total wave function psi of xt is mostly composed of phi 1. That's why average energy is also dominated by your E1. Okay, now what is the probability of measuring the energy E1? Okay, so now you know what is the probability of measuring the energy E1. It means that you have to take the modulus square of this coefficient, because this tells that the probability of measuring particular En. Okay, so for C1 square, you know what is the value of C1, because this is the general expression of Cn. So once you substitute 1 for the value of n, then you will see that this is your C1 square. So this is the probability of measuring the energy C1. Okay, now this is your example 2, where your psi of x0 is given as square root of 2 over 5l sine pi by lx plus square root of 8 over 5l sine 4 pi over L times x. Okay, this is given to you. Okay, now we need to normalize this wave function. Okay, the easiest way to normalize this wave function is to rewrite this wave function in terms of the particle in a box. What I mean that you have to identify what is your phi 1, what is your phi 2, and so on. Okay, so this is clear that this something looks like phi 1, and this looks like something your phi 4, because your general wave function for a particle in a box is psi n pi over L time x, so n is here 4, and then accordingly we have to adjust this prefactor, because in general case it's square root of 2 over L. Okay, so that's what I have said, that this general wave function is written as square root of 1 over 5 times phi 1 of x plus 2 over square root of 5 phi 4x. Okay, now to normalize it, we can add this coefficient square plus this coefficient square and see whether the total comes out to be 1 or not. If this is the case, then the wave function is normalized. Okay, so this is the condition of the normalization that we have seen in the previous slide. So summation over n to infinity mod of Cn square. In this particular case, there are only two values of your coefficient. So 1 over 5 plus 4 over 5 is equal to 1. So it means that indeed this form of the wave function is normalized. Okay, now let's estimate the average energy. So average energy, we have seen this is the expression of your average energy. So we know what is our Cn square for the first case is 1 over 5, and then E1 plus 4 over 5 E4. So this is going to be average energy. Now we can substitute the value of E1 and E4. So this is the value of your E1 and this is the value of your E4, and you can add it. This comes out to be this one. Okay, now this is another subsection of this question. If no measurement is performed, what is the state of the particle at time t? Okay, so then state of the particle at time t will be the superposition of phi 1 and phi 4. If there is no measurement, it means that psi of x and t, where t is any time t, then we have seen that this is our time independent part with the proper coefficient, and then we have to multiply the time dependent phase factor. Okay, so square root of 1 over 5 phi 1 of x e to the power minus I e1 over h cross time t plus 2 over square root of 5 4 of x times e to the power minus I e4 over h cross time t. So this is the state of the particle at time t. Okay, now if the measurement is performed such that the value of energy is measured to be E4, what is the state of the particle at time t after the measurement? So you see that you have performed the measurement now, and the value of energy comes out to be E4. So what is the state? It means that once you have measured and you know that energy is E4, it means that your particle is in state 4. So this is your now psi of xt. because energy is G4, so the state is only composed of this part. Okay, so this is the last question of this module that you have to answer. An electron confined in a box where the dimension of the box is of 0.5 nanometer. Estimate lowest energy level and the energy difference between the second and first level. Okay, so you have to answer because we have given the value of L, and now you have to find what is the lowest energy level as well as the energy difference between the second and first level.